This is a recording of topic-specific items for the um, carry look-ahead adder part 1. So if you have been having difficulties doing this lab within the 80 minutes of the lab time, I would strongly suggest you to watch this video. So we're going to start from the beginning. This is not a solution type of video, but it is a review session so that you will probably be able to look up the relevant information from last week so that you can actually finish this lab if and when and if I give you more time. All right, so first question, and let me just kind of magnify this, or I can turn off the setting screen, which is just taking up space unnecessarily. There we go. And bump up the font size. There we go. All right. So create a main circuit like this, and my screen just blanked out, but that's okay. So to do this part, we have to know how to make a multi-bit input pin, and this tunnel also has to be multi-bit. So in the previous lab, we talked about in the multi-bit um, gate lab. Okay, let me just kind of open a different window so that we can refer back to which lab. And I will just point it out, and you're gonna have to look it up and figure out the instructions of how to do it. All right, so all the labs that we have done so far, the one that we did last week was multi-bit stuff. That one talked about how to make multi-bit pin and multi-bit something. To make the tunnel multi-bit, it is the same way. You extend the same mechanism to do that. Um, all right, and then looking up the purpose of the label of a tunnel, that is in LogicSim's own built-in help. And I'm just using this question to kind of guide people to read the documentation from LogicSim itself. I do not get a whole lot of I do not get a lot of feedback from question number 1, so we're going to move forward to question number 2. So here's question number 2, and the first question was that I get, is do we need to make new labels? And the answer is yes. And is this a new circuit? The answer is no, because the following is a starting point of another part of this main circuit, which means it is still the main circuit, but this is the other part of it. Another part of it, you can put this, below to the right-hand side of what we already have at this point, but the whole idea is this is another part of the circuit. It is fairly common that people do not notice that X, Y, and K0, even though they are the same kind of tunnels as they are here, the phasing is different. Okay, the connection point is right here and not on the other side. So some people may not be making the right connections because they are only graphically connecting the wires, but not actually to the actual connection point of a tunnel. So the question asks you to make the connections between the tunnels and also the other tunnels, PG and PG and Q, and using these specific gates over here. And in the question itself, it says quite specifically that the order is not necessarily right. So P may not be corresponding to this gate, G may not be corresponding to this gate, and Q may not be corresponding to this gate. And here comes the questions, right? Some people ask, where do I find Q? Where do I find G? And where do I find P as definitions? So to those questions, the answer is they are all in binary number addition. Okay, I'm just going to open this up. All right. And this is a long module. And some people would be asking, or some people did ask, so where do I find the definition of Q? Well, that is what I expect people to do on their own, is to read the module, because I did talk about Q in class several times, okay, last Thursday. And I also expect people to be pre-reading and also post-reviewing the material. Um, so that's basically what that is. Okay, you kind of have to wait, you kind of have to find the definition, and this is also why it is helpful to locate all the definitions, or as I talk about the definitions, jot down on the side and say this is the definition of Q, this is the other definition of Q, this is the yet another definition of Q, and so on. Okay, so I'm gonna give everybody a freebie and talk about how Q is defined in the module. So in the module, Q is defined when we introduce multi-digit addition, and Q is the result. So Q is R of xi by I, and R of xi by I was also talked about in class. I used a C function to demonstrate what R is about. Okay, and when we switch to binary, Q is also redefined to be like this. Okay, this is the shorthand of a Boolean expression. So there we go. This is how R is defined, and Q is R of xy. So that should give you the answer. And then somebody may be looking at this and go like, but I don't see a OR, NOT, and AND gate up here. All we see is something that we have not seen before that looks like this. Okay, then you're supposed to be looking at the Explorer window or Explorer pane of Logisim and find out what it is. Okay, that is what I expect people to do, is to basically find the information on their own given the tool that we are already using. So I think that is one of the things that I expect people to be able to do, is to read, jot down the notes, and at least know where to find the definitions. Okay, that is a very basic assumption when I create these lab activities, and it will certainly be an assumption in an exam. Okay, so in an exam, if I refer to something and someone is asking, but I don't remember the definition of that something, can you tell me what it is? The answer is going to be no. I cannot tell you what the definition of something is, not in the exam for sure. Okay. All right. So this is the second question. Some people ask questions about this, um, and then we have the third question. So in the third question, a lot of people. Okay. First of all, this is a multi-bit input pin. So that means whatever is coming out of it is a wire that has multiple bits. And this question does rely on people knowing how K1 is defined in the carry look ahead manner. And then the question is, where do we find how K1 is defined using the carry look ahead mechanism? Okay, this is very spelled out. Okay, and the answer, I'll give you guys a freebie too. That is in section 6. So in section 6, we have K1 being expanded out of this general equation here, and it is G0 or P0 and K0. So now the question is, how do we make this happen? Because the input pin are just P and G, so what do we do? This is why we use a splitter. Okay, so we talked about how to use a splitter from the first lab, and with the multi-bit stuff lab having a more concentrated discussion of the splitter. So that's how you extract the individual bits out of P. This is P0, this is P1, this is P2, G0, G1, G2. So you have to extract the right bits out. So once you have extracted the right bits out, okay, then these are single bit operations. In other words, the OR gate is a single bit OR gate. The AND gate is a single bit AND gate. Okay, because that, oh, I pointed out to the wrong thing. There we go. The OR gate is a single bit OR. The AND is a single bit OR, a single bit AND, because G0 is one single bit. It is bit 0 of all the G's. This is bit 0 of all the P's, and K0 is a single input pin, single bit input pin. So these are all individual bits. In other words, when I created this lab, I was expecting people to understand the concept of a splitter, the concept of a multi-bit wire, the concept of a multi-bit input pin, and the concept of single bit gates versus multi-bit gates from the lab from last week. So now we kind of go back to the lab from last week, because I want to point out that there, instead of just being a lab for people to just breeze through, the questions are intended to teach the concept of multi-bit. Okay, um, so there are explanations, okay, of how multi-bit works, and also illustration of how, the result of a multi-bit thing works. So these are all hands-on stuff to help you understand what is a multi-bit gate, multi-bit input pin, multi-bit gate, and so on, and how they are different from single-bit equivalences. And question number 5 is trying to relate multi-bit gates to bitwise operations. And I received no questions whatsoever over the weekend or during the lab of what is a bitwise AND versus a bitwise OR versus a logical AND versus a logical OR. Nobody asked any questions. So, not being a mind reader, I'm just going to assume everybody understands the concept. So if they understand the concept, then this lab should not be a problem. Really should not. So the difficulty of the third question can be coming from different sources. One, it can be coming from the point of people cannot remember what they did last Thursday. So that means a review of previous labs is going to be important. Two, um, people understand the concept of the multi-bit stuff but cannot relate to what we're trying to solve here. So that is a little bit harder because we have a multi-bit input pin here, and yet we need single bit gates to compute K1. So now the question is, what do we do? On one side we have a multi-bit thing, on the other hand we have a single bit thing. The splitter is the answer. Okay, and so how do people know that they're supposed to use a splitter? For the most part, I'm relying on people to make that connection. But I also wrote here, okay, that grammar is incorrect. Then use splitters to split P and G to the bits that you need to compute K1. That, I think, is making a pretty clear connection of what you need to use, and based on what splitters are for, and based on the lab from last Thursday, I'm expecting people to make that connection to get this done. Okay. And then the next question is to create K2 and K3. So that's basically just more complicated than K1, because if people can make K1 work, they can also make K2 and K3 work. Because K2 is just more complicated and K3 is even more complicated. So I'll give people a freebie. Okay, this is how K2 is defined, this is how K3 is defined. Yes, they look a little bit nasty, but you can also, just use one single AND gate for this, one single AND gate for this, one single AND gate for this. This does not require an AND gate, and then this one plus the output of the 3 AND gates go to the input of an OR gate, and then the output of the OR gate is K3. That's kind of what I expect people to be able to do. All right. So that's kind of a quick um, go through of the lab from yesterday. And I'm still trying to decide whether to let people to work on this again today. Um, but that's the idea. Okay, so the idea is to make connections between the knowledge, that we gain from the modules and the previous lab, and be able to connect those concepts together to solve a problem. Okay, and this is not even problem solving, by my standard. By my standard, this is really a fairly straightforward, direct application of what we have learned. Um, and I certainly usually do not give a whole lot of labs like what we did last week. Basically, this is step one, do this, step two, do this, step three, do this, and then step four, do this. Okay, it's a sequential, we'll just follow the steps to get something done. Okay, that is not typical. Okay, I'm just easing people into this class and have those first few activities like that. Okay, from here on, this would be a fairly representative lab of, from here on. Is, it does require, knowledge that we have accumulated up to that point in class. It requires a little bit of thinking of what tool we need to use. Basically connecting the concepts that we have learned from previous labs. So that's kind of what I have to say. Alrighty. So I'm gonna stop this video recording right now. If you do have concerns, comments, and whatnot, you can direct message me. You can send a message to the to the whole class in the general text area. That's perfectly okay. I'm so that's about it. All right. Thanks for watching.